Hey everyone, Miss Whitaker here, and today's mini lesson is on changes in state. When we're talking about changes in state, we're talking about how materials change between the phases of matter: solid, liquid, gas, and plasma. Now we won't be getting into plasma here, but it's good to be aware that that is a state of matter. So water is on our planet in all the states of matter: solid, liquid, and gas, snow and ice. Liquid water, of course, covers most of the planet, and water vapor is all around us. So it comes into play with weather as well as other atmospheric and geospheric conditions. So when we're talking about changes of state, we're talking about things like melting and solidification, or evaporation and condensation. We've talked about those things in the water cycle before. You can also sublimate, which means going directly from a solid to a gas, and we can also go through deposition, which is when it goes from a vapor directly to a solid. So really interesting stuff. It happens all the time around us. We don't really think about it though. Something that's important that applies to earth science is on the first page of the reference table. It talks about how much energy it takes the system to either melt/freeze or evaporate or condense. Now you'll notice on the front page that it takes far less energy to melt a material than it takes to evaporate or vaporize the material. Significantly larger. And what's happening is that the energy, which is represented as something called joules, gets fed into the system, and that energy goes towards breaking the bonds of the material to make them less structured, right? So we have solids, which are very structured, and as they go through liquids and gases, they become less structured with their atomic structure. So that energy is going into changing the bonds. Now, going the other way, that same amount of energy is released. So when we're going from a vapor to a liquid, the material is losing energy. Just as much as it would take to vaporize, the same amount is lost to go back into the liquid state of matter. And then when it goes into the solid state of matter, it loses the same amount of energy as it would take to melt. So that's important because if you look at the graph that was in the notes, and I'll put it up here as well, you'll see that really flat area when it changes state, and it's significantly longer between liquid and gas because it takes so much energy to break those bonds and to make them less structured. So when a material is going through a change in state, the temperature stays the same. Now that's a really important concept, so let me say it again. When a material is going through a change in state, it stays the same temperature. That's because, again, this is something called latent heat or latent energy or hidden energy. It's not showing up on the thermometer, but the energy is there, and it's going towards changing the state of the material, either going to more structured or less structured, depending on which way we're going across the scale. So another really helpful page in the reference table shows the boiling point and the freezing point of water. So know that's in your reference table. That's something you can refer to. It's something you don't need to memorize, although most of us know it. And I use it a lot as a meteorologist. Working as a forensic meteorologist, as somebody who works with lawyers to do slip and fall cases, temperature is key. So what I look for when I'm doing data is the temperature around 32 degrees Fahrenheit or 0 degrees Celsius. That would cause conditions to freeze. If it's above that, then freezing would not be an issue. The boiling point of water, we know, is 100 degrees Celsius or 212 degrees Fahrenheit. Now that's at standard atmospheric pressure. It's important to know that as elevation changes, the boiling point and the melting point all changes as well. But for our purposes, we're going to say that we're at a standard pressure. Last but not least, we need an energy source for this. And that energy source would be the sun. Mostly. Now remember, the sun is going to power our external processes. Those are things like weather and things that are happening on the surface of the earth. We get energy from the sun because the sun is going through something called fusion. Fusion, think of fusing together. So what happens in nuclear fusion is you have these atoms colliding at super fast speeds. They're combining or fusing, and they become a lighter element, but also a lot of energy is produced from that. It's going actually from hydrogen to helium, to be specific. So those atoms collide together, they fuse, make the lighter helium atom, and then you have to have conservation of mass and energy, so the leftovers goes into energy, and that's what powers a lot on the surface of our planet. The internal source of energy, we do have that, and that's actually really important as far as our development as a planet. So the inside of the earth, we believe, is a sloshy iron and nickel, and we know that based on how earthquake waves travel through the earth. We can make that inference that there's liquid metals inside. So what's happening is that those materials are cooling down and it's going through nuclear decay, which actually produces energy as well. Nuclear decay is a type of fission, and fission, if you think of a fissure, like with earthquakes, a fissure is when the ground splits apart, right? So fission is the same idea. The atoms are splitting apart, and a byproduct of that process would be energy as well.